start this wonderful session that we will have for the next 2 hours on space radiation. We will tackle quite a lot of interesting subjects that we need and concerns and issues that we need to solve before deep space programs and deep space missions. And for that we have extremely talented speakers today. And we will have someone from DLR, Professor Dr. Christine Elweg. We'll have someone from Belgium, myself, and then Dr. Walter Tinganelli from GSI Darmstadt. And then we have 2 bright young scientists, Dr. Björn Basselet and Dr. Nissem Abdeljelil, that will also give some different perspectives about the issue of space radiation. And we will close the session with a roundtable with some of your questions and some of the discussions about the way forward for the next missions. But let's start with Professor Dr. Christine Elweg, who will speak about the Space Habitat Guidebook, chapter Space Radiation Effects. Really a great pleasure to have you.
Thank you, Sarah. So I thought if we want to build a space habitat, we will need a guidebook. And in this guidebook, the chapter Space Radiation cannot be missing. Is it okay? Bit high. So, and I will first give you a little exposure for the astronaut. And then I have a very short introduction into the biological effects of space radiation and the risks that are mostly cancer, cataract, and central nervous system effects. And this space radiation guide, I found it while doing internet search. It is from 1962. So there already there was a need to explain this very complicated radiation field in space quite comprehensively. And this field is composed of ionizing, extremely energetic particles, and they originate from our sun. There we have this constant flow of solar wind and solar energetic particles. They can also come out in big bursts in solar flares. And the other source is, for example, supernova remnants, like double star systems with strong magnetic fields, and they can accelerate particles. And these are the galactic cosmic radiation, and they enter our solar system. So these galactic cosmic rays are highly penetrating particles. We can see the full periodic table of elements there. They are stripped of their electrons and extremely have an extremely high energy. Therefore, they are very difficult to shield. And they also are highly effective in producing biological effects. They fluctuate in their intensity with the solar cycle. So the sun produces a magnetic field that protects us from the galactic cosmic radiation. And in solar maximum, the flux can be 3 times lower than in solar minimum. And you see that most of the radiation is protons, and then the next is alpha particles. But we might find everything up to uranium. And the other source, the sun. Here we have mostly low to medium energy protons, and these can be shielded. But in a flare, high dose rates are possible, and the frequency of the events correlates with the solar cycle. The Earth is protected from this radiation by the magnetic field, but this also means that particles are trapped in this radiation in these belts. And here we have mostly lower energy particles in the outer belts. It's mostly electrons, here in lilac. And in the inner belts, the green one, we have mostly protons. And the South Atlantic anomaly is very important for the dose accumulated on the ISS, a part of the inner belt coming closer to the Earth. So what does this mean for the astronaut in terms of exposure? The galactic cosmic rays cause a chronic whole body exposure to a low dose for the whole body, but if we look at the microscopic level, it will be a very high dose. Can be up to 100 of gray. And this exposure depends on the solar cycle, as I explained before, and the shielding situation, which can be very bad, for example, in a spacesuit. And it's composed of the single energetic particles like electrons, protons, alpha particles, and heavy ions. And we cannot turn this off, so we have a 24/7 exposure on ISS and also on exploratory missions. And these particles interact with the hull of the spaceship and produce many secondaries, including neutrons. And then we have the trapped radiation. On ISS, the astronauts have an intermittent whole body exposure to low doses. And this is because the ISS traverses the South Atlantic anomaly, and it contributes up to 30% of the dose on ISS. For exploration missions, the trick is to go fast through these belts and to have only short whole body exposure. And when there's a solar particle event, the shielding is very important to avoid the risk of a high dose whole body exposure to protons. High dose rates can be achieved, and it can be very dangerous if the astronaut is on an extravehicular activity outside low Earth orbit. So we have measurements at different levels. I think Darmstadt is quite comparable to Cologne, the dose rate 0.1 microsievert per hour. And if we go higher up to the ISS, it's already a factor of 250. And if you compare that to the measurements we did on Mars in the MSL-RAD project, together with the University of Kiel and the Americans, we see that the dose rate is quite comparable, but the radiation field is composed a little bit differently, as we don't have this trapped radiation on Mars. And in free space, you see the big problem. So we have there the factor of 770 compared to what we have on ground. So coming back to this nice space radiation guide, there was also a chapter about biological effects, and it's really, really short. And if you look in detail, the first part is radiation physics only, and no biology. And the biology is explained in 7 pages only. And if you look in detail what they write, they say, oh, it's an enormously, there are enormously energetic ions of high atomic number in the radiation of cosmic origin. And the danger potential was recognized only in 1949. And they also state that the eye lens is highly susceptible to ionizing radiation, and they predict the hypothalamus as a sensitive organ. And they also state that the sensitivity varies considerably from individual to individual. So it's interesting to see the progress over the last 57 years since this guide. So I can only show a little bit of that. Concerning the physics chapter, it's important to understand how the energy of these particles is deposited in matter. So you see that with increasing that of the ion from proton here to calcium, the ionizing density increases, and we also have some delta electrons coming out, making a really large track that can damage biological material. And this is quite difficult to measure, so we always rely on linear energy transfer to describe the radiation. This is the mean energy loss of the particle along its path. And it is given in kV per micrometer. So I will refer to this when I show the biological effects. And then the particles go through matter, and a good approximation to the human body is water, because we are composed of water, and they deposit their energy first quite steadily, but just before stopping, they deposit the residual energy that they have on a very short path. And this is so-called break peak. And in this break peak, we can have even more complex damages. And you also see that this break peak and the penetration depth depends on the energy and on the type of the particle. So when we look at the interaction with DNA in the cell nucleus, we can visualize this by using green fluorescent protein tagged repair proteins. And so when a particle goes through a cell nucleus, these repair proteins will accumulate around the damage and indicate where the damage is and how fast it is repaired. So you see this nice green track. And these damages to DNA are very difficult for the cell to repair. Here you see a typical repair curve after X-ray exposure of fibroblast. So we have a first fast repair component, and then a slower one for the more difficult to repair damages. And when we go to charged particles, we see that the cells have really difficult to get rid of this damage, and that the residual damage after 1 day is much higher compared to X-rays. And now the cell will cope actively with this damage. It will activate pathways. And the pathway we looked at is a typical stress pathway, pathway also involved in the immune response. And this is a nuclear factor kappa B pathway, and it can be activated when there's damage to the DNA in form of double-strand breaks. And then the cell will have a survival advantage, and it will communicate with other cells via cytokines. And it also influences the repair of the damage. And we looked at many different ions, how strongly they activate this pathway. And as you can see here, the range of linear energy transfer where they are very strong in activating it is quite narrow. It's a range of around 50 to 300 kV per micrometer. But these are particles that we have in space, and they are up to a factor 10 more effective than radiation qualities that we have on Earth. So that means that heavy ions are very effective in activating signaling pathways. And when such a signaling pathway is activated, it means that target genes can be expressed. And in this study, we looked at 9 different target genes of NF-kappa B. And looked at the effect of different ions. They are represented only by the LET here. And these particles were more affected in most cases to induce the expression of these cytokines and adhesion molecules than X-rays. And so it means that the heavy ion produces a genotoxic stress in the cell. It activates NF-kappa B, and it can, for example, induce a chemokine and cytokine expression, so that it hit cells can alert neighbors that they have been hit, and maybe also transfer damage to non-hit cells. So in this guide from 1962, it was said that the danger potential of these heavy ions was recognized in 1949. And what can be this danger potential? Here, these are older data for transformation of cells, which is a first step towards cancer. And it also shows a dependency of the transformation efficiency depending on the linear energy transfer. And this overlaps quite well with the range that I have shown for the signaling pathway activation. So we use this term of relative biological effectiveness to compare the heavy ions to a reference radiation like X-rays or gamma rays. So this transformation is a first step towards cancer. And so we have to be afraid of cancer risk for the astronauts. And how to quantify this risk. We need to know a lot about the exposure scenario, so the dose that the astronauts are exposed. So the duration of the mission is very important, and what kind, how the body is exposed. So on ISS, of course, it is always a whole body exposure. And the dose rate is important because we have this repair capacity, and if we give the cells time to repair, the damages might not be so detrimental. But it's questionable whether this is really true for heavy ions. And the shielding of the spacecraft, the solar activity, and whether the astronaut is outside in a spacesuit is important, and the type of radiation. So we have this very complicated mixed radiation field with proton and alpha particles, heavy ions, and secondaries. And then we have to look at the individual, the differences in individual sensitivity, the age, the sex, and the health status. And of course, we have the other space environmental factors like weightlessness, we have the confinement, we have disturbed day and night cycles, and we have maybe different atmospheric pressure and composition. So this is a quite popular slide from Durante and Cucinotta. It has been shown for many times, but I think it visualizes very well where we are now with the cancer risk and the uncertainties of these predictions. And what we are doing at the moment is ISS missions. So here we have a calculated risk of 0.1 to 2% additional cancer risk. And NASA says 3% additional risk, lifetime risk for cancer is acceptable. So we will exceed this limit with the Mars mission. And this is a calculated risk. And when we look at the astronaut population, it could be asked whether we find more cancer in the astronaut population. And this is very nicely shown in the longitudinal study of astronaut health, that it is not the case. here astronauts were compared with the personnel of Johnson Space Center and with the population of Texas in a special region. And compared to JAC personnel, we have a little bit more tumors, but the population is too small to, that this is significant. And when we compare these groups with the Texas population, they have less cancer. They are a very selected population. We have a strong healthy worker effect. So at the moment, we have no epidemiological evidence for an increased cancer mortality in astronauts, but these studies does not include ISS data. So we have to wait for another 30 years to have data on the long-term missions concerning cancer, because the latency can be decades for cancer. And the other point in the space radiation guide was the eye lens is highly susceptible to ionizing radiation. Also here were some studies on this, and looking at the cataract incidence in nearly 300 astronauts. And cataract is a quite common alteration, so the incidence is about 20% in European populations. And so the study compared two groups of astronauts flying in high inclination and in lower inclination, and this correlated also with the dose. And you see in the higher dose group, there's more and earlier cataracts. And from these data, Gucinotta calculated a probability of cataracts. And the problem here is that the probability goes up already in the first 3 years, so the duration of a Mars mission. And it is true, the eye lens is highly susceptible to ionizing radiation because it's a special organ without blood vessels. It has no mechanism to remove damaged cells, and it grows lifelong in this germinative zone, producing new cells. And if these cells are irradiated and cannot repair all their damage, they might migrate to the posterior pole of the eye lens and might not differentiate correctly, meaning that they become transparent. So they have to remove their cell nucleus and elongate and produce crystallites. And this is the beginning of a cataract. So we have effects on the eye, and space radiation is a radiation that we can sense. The astronauts can see it. For all other radiation, ionizing radiation types, this is not possible. We have no sensors for that. And this was already described on the Apollo missions. And there were many studies on counting these light flashes. And so astronauts see it when they are dark adapted. And so this raises questions for the astronauts. And Ellie Blakely from Berkeley lab was asked once by an astronaut while she was training him in space radiation biology, if these particles pass through my eyes, do they pass also through my brain? So you see how concerned the astronaut was about this idea. And of course, yes, they do. They are omnidirectional. And we have had this statement in the space radiation guide that the hypothalamus was predicted as sensitive organ. 57 years later, the brain is really in focus, as also called space brain. It is not the hypothalamus, but the hippocampus, which is a very sensitive region. And the idea is that galactic cosmic rays and also the particles of the sun can produce neurodegeneration, and this was shown in many rodent experiments that they have problems with spatial learning and behavioral tests were also changed, and that there are changes in the hippocampus. So this is a very important topic, and also the individual sensitivity. If you search for individual radiation sensitivity on PubMed, you will find 20,000 hits, and for susceptibility a little bit less, because this term is not so well known. And we have some ideas where we have differences, because especially between the sexes. So for the brain problem, there seems to be a difference in the microglia, that in males the microglia is more aggressive and produces more damage when there are particle hits. Another example is breast cancer in females. And this is already integrated, so the sex differences and age and smoker, non-smoker, never smokers is integrated in the NASA cancer risk model. Not yet the genetic background or interaction with other space environmental factors. So microgravity has been researched a lot on interactions, but what about the space fever? So we know that hypothermia is used in cancer therapy in combination with radiation, and it sensitizes the cells to the radiation effects. So this is maybe something that we should look into also. So breast cancer, we have a new experiment going on the Artemis mission, the first uncrewed mission to around the moon, where we will fly together with NASA, Lockheed Martin, Stemrad, and the Israeli Space Agency 2 female phantoms. So for the first time, we will quantify the organ dose for the female breast. And also, the company Stemrad has developed this radiation protection vest. So we will see the difference in radiation exposure in the torsos with and without the vest during flying around the moon. And this radiation protection vest is designed to protect from solar particle events. Of course, we cannot predict that for this mission, so we will mostly see the background from GCR. But the protection from solar particle events is very important, as up to deadly doses can be accumulated during a large flare, as you can see from that here, between Apollo 16 and 17. So this risk from solar particle events is very low in low Earth orbit, and we have there space weather warnings, especially for EVAs. And when we go beyond LEO, there we have the risk of high acute body exposure, so we need a warning system from that and a shelter. So this is a summary of the guidebook, bringing all together the two different radiation qualities, the late and chronic effects, the acute effects that we have to fear, and what is underlying this. So concerning the late and chronic effects, we have to do more about research more the disease mechanisms, the biological effectiveness of the GCR, and especially the individual radiation sensitivity, to look into improved risk assessment and countermeasures. And for the SPI, we need the warning system and symptomatic medication, and colony stimulating factors are already available to treat acute radiation syndrome. So I would like to end my talk with a nice result from satellite flying over the Earth since January in a height of 600 kilometers. And you see here nice the South Atlantic anomaly, and also particles from the outer radiation belt, which you cannot see on ISATs because the inclination is too low. That's it.
Thank you so much. Thank you so much for this wonderful presentation and introduction about the space risks and the space health effects. It was really important to pave all this information about what we are facing. And I'd like to move on to a kind of complementary presentation to the one of Professor Elweg, and entitled, if you could put the presentation, please, entitled Protection Against Space Radiation. Okay, so we are now in a big and in a very challenging period of time where the different international space agencies are really aligned in order to go back to the moon and thereafter go to Mars, which is a very exciting period to live in. And so we know that the intention is to extend the number of and the duration of the missions. And if we look at the history, we go from about an hour and 40 minutes from the first orbit of Yuri Gagarin. Skylab missions in 73-74 were about 10 days, followed by the Mir station program with missions from 2 to 16 months. And then on the ISS, since more than 20 years and hopefully for another few years, missions from 10 days to 6 months, even longer, as we have seen for some Russian and American astronauts, even to above a year. But the objective is in front of us, and strategy is in front of us. The way forward is to go to the moon, settle on the moon, to have a permanent basis on the moon, and then thereafter, hopefully, to Mars. But there is still quite a lot to tackle about that. And we know from the sessions, amongst others, the session of this morning on space physiology, that there is quite a big impact on human health. And so the longer the duration of the flight and the mission, the more impact on the body. So we are now aligned for this big endeavor, the Deep Space Gateway, which would be the first human spaceship to explore the solar system, the most distant human space missions ever attempted, and the testing ground for challenges of long-term space duration in deep space. And we have, as already mentioned clearly, we have to face and we have to find a way to adequately countermeasure and counteract the impact of radiation, which is the #1 showstopper for this long-term mission. So here an article entitled Space Radiation, the #1 risk to astronaut health beyond low Earth orbit. As beautifully explained by Professor Elweg, space radiation is very complex. It's very mission dependent. It's depending also on the activity of the sun, and so it's continuously changing from mission to mission. And we will see that has an impact. And one of the first things which is very important to perform is to characterize and to measure this radiation. So space radiation can be divided into 3 big categories of solar wind. Solar wind is not a big hazard. It's an hazard which is considered as a low hazard, being stopped by the code of the space vehicle. It's composed of low energy electron, protons, and alpha particles, but it's a continuous flux. However, solar particle events are a matter of concern when this activity of the sun, when you have a solar flare, you can have a burst and a very high flux and a very hazardous flux intermittent of 1 to 2 days of high energy protons, and we'll see what is currently developed as technology and methods to avoid and to protect from these solar particle events. And where we still need really a lot of research is for the galactic cosmic rays. For the galactic cosmic rays composed of protons and alpha particles as well as heavy ions. This is a continuous flux. This is hazardous. We don't have complete solutions for stopping them, and so we need more research, and I will give you some update about where we are now. On the bottom left of this picture, you see, as already illustrated by Christine, the impact on the DNA. And the fact that basically you see that when you have heavy iron, they leave a track, and this track induces DNA damage. It can be a single-strand break, it can be a double-strand break, it can take just a few minutes for the cell to repair, but it can take also hours and sometimes days to repair. And in the second picture down, you see this track induces what we call complex DNA damage. And complex DNA damage is when the DNA is damaged very close and in a high concentration in a certain area, and that makes the cells a higher difficulty to repair, with a higher risk of misrepairing. Misrepairing meaning maybe an induction of mutations, and as explained by Christine, this induction and this accumulation of mutations can lead to diseases like cancer, but also other diseases. Another important issue is to choose well the material that to shield because of the production of secondary particles coming from the material, from different types of materials. So where we need to be very careful in choosing and in being able to have maybe some material that can induce the production of secondary particle, but then stopped by shielding material, as we will see in the next few slides. So one irradiation can produce a myriad of secondary particles. So this is also something important to remember. When we look at the dose rate and calculated dose and global dose, data can vary from studies to studies, and one of the main issue is the fact that they are very mission specific, depending on the solar activity, depending on the movement and the attitude of the ISS. So these missions might give different results in terms of radiation dose. So Christine mentioned a factor of 250 higher doses of irradiation on the ISS, on the International Space Station, in comparison with the Earth. From our studies, we revealed a factor of 165. Some other studies showed a factor of 150. So it just the value is not fixed. The value is not a pure absolute value. This value can change depending on the mission. But if we, as we plan and as is being prepared by the scientific community, go to the moon, we are going to face higher doses of radiation, higher dose rates, with doses that will be about 300 times higher than on the Earth. And even further, during deep space missions and going to Mars, we will have to face, and coming back from Mars, we'll have to face even a factor of 1,000 times than on Earth, which means higher damage to cope with for the cell, to repair, and with a higher risk of misrepair. So how can we deal with that, and how can we improve radiation resistance, or how can we increase the protection of the astronauts? There are different ways. There are different ways, and all these ways will be explained now more into detail during my presentation and the next ones. So one way is to enhance shielding and maybe find ways and composite material that can shield better. Usually to shield better, you need very small atoms. Hydrogen is a very good atom to use. Boron is a very good atom, so mixtures of boron, hydrogen is good. Using water is also a possibility. For the moon, we would need, unfortunately, a layer of 13 or 12 meters of water to stop the galactic cosmic rays. So it's quite a thick protection, and we'll go through the shielding later on. Then there is this aspect about the radiation resistance of individuals. We are not all equal in front of radiation. Some of us are quite sensitive to radiation. Some of us will be very resistant towards radiation. So is there a way there to personalize the different programs, space programs of the astronauts. And for that, we are part of an ESA topical team that specifically look at a personalized program. So taking into account the projected sensitivity of each astronaut and developing program. Why these programs are important? Because in the next missions, and especially the missions to the moon, quite a lot of extravehicular activities are foreseen, and so the astronauts are going to go out of the moon base, and it's predicted that they would go between 50 and 70 times out the moon base, which means that there they won't have much protection except the spacesuit. So an extra attention is now paid more and more on the composition and the protection given by the spacesuit. But on top of that, we will go through this individual susceptibility, which is not only very important for astronauts, but also on Earth for our radiotherapy patients. Then there are different ways using pharmacological compounds, using radioprotectors that start to give some quite interesting results of protecting the bone marrow. The bone marrow is the most sensitive part of our body. It's the site of production of our blood cell progenitors, the white blood cells, red blood cells, and platelets. And some good results are obtained. Are they already extrapolable and translatable to space missions? Not yet, but work is done in that way. Then we will also tackle the issue of biomarkers of radiation susceptibility. And we will see what are the different types of biomarkers that we have at our disposal on the day of today. Biomarkers of short-term exposure, long-term exposure, long-term effects, and late effects. And then hibernation, we'll have a special talk just after mine about this particular and interesting topic. And then the biobanking regenerative technologies will be tackled. So of course, as mentioned, on the Earth we are cocooned. We are very well protected, where 99.9% of space radiation is stopped by our atmosphere, by our magnetic field. But this is not the case on, This is not the case on the ISS. Here on the ISS, I put as a value 150 times more than on Earth. The distance is 300 to 400 kilometers. And there on the ISS, a lot of the scientists that are here in this auditorium are sending and preparing and performing experiments in order to understand the impact of space conditions on human health, amongst others. And for what concerns our studies at the Belgian Nuclear Research Center, where I work, we have radiation detectors that are placed inside and outside the International Space Station, and we are also monitoring and following up the astronauts' health, and specifically on the immune issue, on the immune system, but also on their radiation susceptibility, in order to understand how do they repair? Do they repair as fast when the DNA damage induced by radiation, by space radiation? Do they repair as fast when they come back from a mission to the ISS or not? Do they have as much misrepair? Do they have a higher misrepair? And do they have higher level of mutations? And what is going on in their body after a mission of 6 months? And then, as maybe some of you know, we're also in Europe, we are also very active to develop life support systems using organisms like bacteria and like plants in order to produce oxygen, to recycle water, to be able to produce food. And this is very important, and SEK, Belgian Nuclear Research Center, is playing an important role in that. We also flew in July the first experiment for lunar agriculture. So understanding how bacteria can use basalt, lunar basalt, in order to purify, to extract and to concentrate different minerals that are present in this basalt. So very important to improve knowledge in order to tackle radiation impact. It's important to do monitoring, to do the characterization, and to understand space radiation, how it penetrates inside the space coat, the space vehicle. How does it penetrate? And it's important to do that actively, to measure actively radiation and also passively. So for that, together with the DLR and other institutions, we are continuously monitoring radiation, passively measuring the whole mission dose of radiation, and actively being able to give online information about the dose of irradiation at that moment, at the precise moment for the astronauts in order to go to a more protected area. And it gives you here a picture of a Belgian astronaut, one of our national heroes, Frank de Win, placing some of our detectors inside the Columbus module. Okay, so in case of solar flares, in case of high activity of the sun, there are for the moment three compartments in the American and in the Russian segments of the ISS that are particularly well shielded. And one of them is as you see in the center, the water wall. And the water wall is really the reserve of the water for the astronauts. So it's a few cubic meters of water, and as I mentioned, the small atoms like hydrogen are very important and very useful to stop the cosmic radiation. And so this is one of the places. Another place is the sleep station, where the sleeping environment is also surrounded with polycarbonate, and polycarbonate is polyethylene, and polyethylene is composed of carbon and a lot of hydrogen. So hydrogen stopping also part of the radiation, so also very useful. But if we go to the moon, which is the intention, the dose of irradiation will be higher, 300, 400 times higher. The moon is the archive of the Earth's early history. There is no magnetosphere to protect, so no protection from harmful space radiation. It will be the springboard and the testing ground before Mars, and the Moon Village will be the first step before Mars. This week, the directors of the different space agencies are gathering in Japan. It's a meeting organized by JAXA in order to review the architecture of the Moon Village. And right now, as you can see in this picture, the Moon Village seems to be kind of at the surface of the Moon, not so much underground, whilst underground would be maybe more protective against radiation. So this is the very last pictures from 2 weeks ago, giving the architecture of what would be the Moon Village. That will be an endeavor from different space agencies, and I hope that the meeting that will take place this week by the different directors of the space agencies will hopefully make a move forward into this architecture and choice of architecture and the mission objectives on the moon. Another attention that I would like to give here in this presentation, and maybe we can continue tackling that during the session, the Q&A session afterwards, is the extravehicular activities. So, as mentioned, the extravehicular activities were quite short, especially here during the Apollo program. From the Apollo 9, 2 hours of extravehicular activity, to Apollo 17, 22 hours of extravehicular activities. What we are facing and what we are preparing is the future, the moon base, where it's foreseen to have about 30,000 hours of extravehicular lunar exploration in an extreme and in difficult environment. And so far, no astronaut has ever performed more than 3 lunar EVA, but future astronauts will have to do many more EVA, so extravehicular activity than that, with about around 70-50 lunar extravehicular activity during their mission of 6 months. And so when they go out, you have this spacesuit, and this spacesuit needs to be resistant to abrasion of reactive chemical dust, of the regolith, of UV, temperature, oxygen, and weight. So also a great attention will be devoted to the walking, to the flexibility and elasticity. Different components are being tested with Gore-Tex, Kevlar, Teflon polycarbonates that are tested for the moment, but still quite a lot of research to be performed in order to allow these missions. As already mentioned, radiation is quite tricky in the way that it can induce very short-term effects, but also long-term effects, like cancer, decades after exposure. Short-term can be also mentioned as acute effects. The most visible and the most dramatic acute effect is the acute radiation syndrome. This is what some of the survivors of Hiroshima and Nagasaki have experienced after the atomic bomb. The way the body will react in sequence, with the bone marrow being very sensitive, as I mentioned, so with a depletion and a decrease, dramatic decrease of white blood cell progenitors, red blood cell progenitors, and platelets, decrease of the blood count, and the blood formula, which can be quite fast in a matter of a few days. Then in the acute radiation syndrome, the next sequence of event after the bone marrow is the gastrointestinal tract. So the gastrointestinal tract, and this is also mainly due to the presence of stem cells. And the stem cells that are highly proliferative are also very radiation sensitive in general. So this is due to a dogma in radiation protection called the dogma of Bergonier. And Bergonier, early in the 20th century, showed that cells that are dividing very highly and very much are also more sensitive to radiation. Apart from this acute radiation syndrome, there are also other risks, like inducing cancer, so inducing carcinogenesis. Different types of cancers are reported to be induced following exposure to radiation, like lung cancer, breast or colon, stomach, esophagus, and leukemia, and liver, and ovaries, and bladder, and skin, and brain. Christine mentioned already the central nervous system effects, the effects on the brains, with some acute and late changes in cognition due to the impact on the hippocampus being the parts, the site on in the brain, site of memory, of learning, of spatial orientation, and being very susceptible and very sensitive to radiation. But also playing an important role in motor function, and also in the mood and in the behavior. So this killing or this impairment of the hippocampus can lead to different types of diseases which are not cancer related. Then we have the cardiovascular system, where you can have a higher increase of cardiovascular disease, are a model for accelerated aging for many aspects and for many tissues. This picture shows also the higher risks that will be induced by longer missions. As you can see, the dashed red line with 1 millisievert gives the idea of the exposure of the population on Earth. But you see that Mars, you see where Mars is located, where the Moon, we increase very much the risk of a few hundred times higher risk on their health. This picture I'm not going to go through because it's been shown already by Christine. And this picture shows you the radiation sensitivity between people. And if you look at the normal radiation range, radiation susceptibility range, you have a Gaussian curve. But on the left and on the right of this Gaussian curve, you have people who are going to overreact, usually patients after radiotherapy, that you can notice after a few days of radiotherapy, you can have a very high impact already seen on, for example, on the skin. So you have a percentage of very extreme and severe sensitive people. Radiation sensitivity change and with age. So the most sensitive organisms and age are the embryos. The embryos where the development, the cell cycle is extremely fast. In early embryogenesis, you have a development and a cell cycle of about 8 hours. Whilst in adulthood, you have the typical cell cycle of about 24 hours. So radiation susceptibility decreases with age. So this is also a parameter we will probably need to take into account when going back to the moon and to Mars, to maybe, as you can see here on this table on the left-hand side, that from an age of 50 years old, you decrease very much your radiation susceptibility, whilst if you take someone who is much younger, you have a much higher risk of inducing DNA damage and misrepair. So it's important to do this kind of studies, or that we do already at the Belgian Nuclear Research Center. We are monitoring this radiation susceptibility in astronauts, not to do a selection of the astronauts later on, but to individualize their program of radiation exposure during their mission, and maybe to give some advice like limiting or giving some advice on the maximum number of extravehicular activities that these astronauts should make. And maybe not, if this astronaut is very sensitive to radiation, to have a lower number of extravehicular activities. Very important also is that there is a crucial need for harmonizing between all the space agencies, the tolerated threshold, and to decide harmoniously for all the countries what would be the threshold we will tolerate, threshold of radiation, the maximum level of radiation that we would tolerate in all astronauts, whatever country they are from. So, and this is an important work which is taking place now. There is a working group from the International Commission for Radiological Protection in order to try to harmonize between the different space agencies, because as you can see in this table, the risks and the thresholds are not the same for NASA astronauts, not even the same between females and males, and not the same for JAXA astronauts, and whilst for ESA, for the Russian and the Canadian astronauts, it's one standard risk, male, females, whatever the age. So there is a necessity to improve radiation resistance. There is a necessity to develop biomarkers. And to develop the best biomarkers, biomarkers is any measurement reflecting an interaction between a biological system and an environmental agent, which may be chemical, physical, and biological. There are different types of biomarkers. Biomarkers of exposure, biomarkers of sensitivity, susceptibility, and biomarkers of late and persistent effects, with very important possibilities to use these biomarkers for nuclear accidents, for example, for in case of nuclear terrorism, for astronauts, of course, but also for radiotherapy patients, in order to adapt the protocol for example, radiosensitive patients or radio-resistant patients. So there is a large community of radiation biologists that gathered and wrote a Bible that you saw in the previous slide, which is here. So ionizing radiation biomarkers in epidemiological studies, published in Mutation Research in 2017, and so there are different categories, biomarkers of exposure that will give you a clear idea depending on the exposure and the time of exposure. The biomarker of susceptibility, it's to be able to recognize a susceptible patient from a non-susceptible patient to radiation. A biomarker of late effects, it's a biomarker to detect early enough in a patient, in a person, the risk of developing, for example, late effects like cardiovascular diseases, and biomarker of persistent effects that can last for more than 1 year. I'm not going to go too much into detail because of sake of time. We can go back to this discussion afterwards. So this is just a very maybe complex but interesting way of presenting all these categories of biomarkers, these 4 categories, as I mentioned. And in red, these are the categories that we're working at the Belgian Nuclear Research Center, but these are the main categories that will most probably be used for astronauts but screening, monitoring, and programming for individualized program of missions. Okay, so as I mentioned briefly, the type of DNA damage, this complex DNA damage is a very much issue that many scientists are working on. We have different facilities in the world, and one that we use at the level of Europe is the GSI. We also use the GANIL. These are beautiful big instrumentation that allows us to irradiate with different heavy ions, different types of protons. And we know that galactic cosmic radiation are densely ionizing along the particle track. They can cause unique damage to biomolecules, distinct patterns that we really need to identify of DNA damage, and distinct profiles of oxidative damage and repair length. So all that needs to be carefully monitored at the level of the cells, at the level of the tissues, organs, and at the level of the whole organisms. A big concern is the fact that there is no human data that exists to estimate the risk for heavy ion found in space, and that animal and cellular models with simulated space radiation must be used to gain new scientific knowledge, and that we don't know also if there are potential additive or synergetic modifiers of risk. So it's important to improve the knowledge on radiation resistance. It's important to monitor the radiation susceptibility of the different tissue. Some examples here from skin tissues, and there is a poster from the Belgian Nuclear Research Center from Elin Radstak speaking about skin experiments, where you clearly see the number of spots on the right-hand side on space samples that shows the higher damage and more complex damage in samples of skin cells in space conditions. Another tissue which is quite sensitive to radiation is the cardiovascular system. So it's important also to study at the cellular level. And this is an experiment we have performed 2 years ago that flew in 2016 with Tim Peake, the British astronaut, in order to understand what is the susceptibility of the blood cells and the blood vessels. Brain, as mentioned, is also sensitive to space conditions, and it's important that not only you don't lose brain cells, but so it's the quantity, but also the synapses, the connections between cells needs to be of high quality. And here you see that even with low dose of irradiation and being in a simulated microgravity condition, you can impact the neuronal network quite a lot by decreasing the number of cells in space conditions, but also by decreasing the synapses and the length of the neurites, which is the length of the arms of the neurons. Also, to improve radiation resistance, we need to understand what other organisms have developed as radiation resistance mechanisms. So for that, here a beautiful organisms, which is a rotifer that will fly at the end of this year in December, but also in April next year. And the rotifers are extremely radiation resistant. So from these data, we hope that we will understand better how these organisms are facing and repairing, and how can we implement that maybe in humans. As I mentioned, ESA has got this beautiful facility of GSI, and a particular program of ESA is devoted to the investigation of biological effect of radiation. So where we can decipher cell type per cell type the impact of radiation. And there are other facilities also at SEKCN that for which you are welcome to join if you want to study different types of irradiation. So to finish, astronauts are radiation workers, are nuclear workers. So a very important principle in radiation protection is that we have to follow the Olara Principle in order to protect them the best we can. And the Olara Principle means as low as reasonably achievable. So one way is to harmonize those threshold and to decrease as much as possible the risk for the astronauts to an acceptable level. So it's our duty to, and how do we implement this Olara concept in developing real-time radiological support, in understanding and minimizing exposure to radiation, in understanding the effect of space radiation on material, on the biological and processes and biological systems, and to develop human support technologies and advanced systems. Okay, so, and if you haven't had the opportunity yet, I would like to invite you to some of our posters that are being shown. We have first an oral presentation that will end up this session on the Hindlimb unloading model. And we also have some poster on skin effects, on using space conditions for fighting against cancer, a presentation on cardiovascular system, and another presentation on heavy iron particles, so cancer therapy for better treatment of cancer. And space is a marvelous inspiration thematic of research. And here is one of the, on the left-hand side, the first book of a trilogy, To Reply, No Reply, of Peter Hackers, in which it's a Mars mission, preparation of Martianauts and coming back, and in which he mentioned the Belgian Nuclear Research Center, and in which I'm very honored to be one character in this book. And if you would like to have more information, you can also follow the TEDx conference on space radiation matter that was recorded last year. And with that, I would like to thank a few people. Some, my institution, Belgian Nuclear Research Center, our national financing source, the BELSPO, Belgian Science Policy, ESA, the European Space Agency, the International Polar Foundation for our Antarctica mission, and a few people that you can see on the left-hand side. And thank you very much for your attention. Okay, so without waiting longer, I would like to invite now Walter Tinganelli from GSI, who will speak about hibernation. Thank
you. Hello, good morning. It's a pleasure for me to be here in Asgardia. I like the idea to contribute even in a small part to paving the road to living in space. And today I will speak about space radiation. It was already said a lot about that, so I try to be fast in this about space radiation, and then I will speak about hibernation. So I'm Walter Tinganelli. Could synthetic hibernation be used as an alternative method to overcome the space radiation issue? We said in this conference many times, that space is an hostile environment. We have confined space. We have noise, the background from computer and device on board. We have isolation from family, friends, from the rest of the world in principle, dietary limitation, circadian rhythm disruption. But the most, I would say, important stressor in space are microgravity and radiation. It was already said about the puffing phase with the microgravity because of the fluid that moved to the head, and then we have the bird leg. We have visual impairment, we said today. And we said also that in space, of course, because of microgravity, we have problem with bone demineralization and muscle strength, so the astronauts lead a lot of exercise during their mission. In space, then, we have galactic cosmic radiation that is completely different from radiation that we have on Earth. This we already heard. And we have essentially proton, helium, and some heavy ions. The contribution of the heavy ion decreased, but the equivalent dose is still the same because these are able they are the major contributor to the total equivalent dose. We are around 100, 300 times higher. The radiation in space is 100, 300 times higher. Radiation in space is isotropic, so it comes from everywhere. And we also have been heard that it depends a lot on the solar cycle. We also saw this picture, and we saw a different movie, but in principle it's the same one, where we have here this 2-track of iron traversing the nucleus of a cell. And here you see this is a sparsely radiation, so here gamma ray, compared to silicon and iron. And you see, as was told already, that here we have this ionization produced a sparsely DNA damage. Every spot you see here is a double-strand break, but when you see with the heavy ions, silicon and iron, you see that the complexity of this double-strand break increase, and then the cells has more problem to repair this damage, and then the cells is going to die or to be very high mutated after irradiation. Plans for exploration and colonization. So it seems that now around 2021, the idea is to have a flyby around the moon, but then the next idea is to have the moon base, to have the Mars base, and then there are more ambitious plans to go on asteroids or even on satellite like the Jupiter satellite Europa. So very far. And we see that we go, the further we go from the sun and this magnetic field, the more the radiation increases. So we are around 1 millisievert per day around the Earth. When we consider the background is 3 millisievert per year. So here we have 1 millisievert per day, 2 millisievert per day, and then 3 millisievert per day as far as we go from the sun. Because as already been told, we have that the heliosphere of the sun is able to stop the galactic cosmic ray, and there is a nice result from the Voyager 2 that for the first time went out of the solar system, and we see here these are the galactic cosmic ray, and this is the solar wind. You see immediately after when he went out from the heliopause, we have a decrease of the solar wind and then an increase of the galactic cosmic ray. In a hypothetical mission to Mars, we will have every cell traversed by 1 proton every 3 days, by 1 helium every 30 days, and then we will have most of the cells of the body completely traversed by heavy ion. Which are then the space radiation risk? We have seen acute syndrome for solar particle event. In principle, these are produced by the sun, and they are not very energetic. So in principle, if the astronaut is in an EVA, extravehicular activity, of course, will be highly exposed to this radiation. But this is, if he is inside the shuttle or the International Space Station, then will be quite protected. Then we have cancer and tissue degenerative effects. About cancer, we have seen this picture already 2 times today. But you see, here for Mars mission, we have that this diamond that is the risk of cancer death expected, that is around the 3% more. But we have a big error bar, as we have seen. And this big error bar, it comes from many factors, but the most important one is radiation quality. So we don't know, we have not so much data about DNA and tissue damage with the very heavy ion. About the tissue degenerative effect instead, what happened to your brain on the way to Mars? Here is this nice experiment with mice where in principle they checked this behavioral test. So we have novel object recognition and object in place, where in principle the mouse is able to recognize new object inside the cage, or that 2 objects are moved inside the cage. And then you see when they irradiate these mice with oxygen and titanium, even with a very low dose, there is a decrease of disability in mice, so a strong cognitive decrease. It's also true when they look inside the brain of this animal. So here you see in green the neurons. And then you see after irradiation, there is this red, I don't know if it's so clear, but this red spot here, in principle, these are the spines. So the connection between the neurons, and then decrease a lot after irradiation, like decrease a lot also the dendritic branch, the complexity of dendrites, and the length of the dendrites. Also about the heart, here there are data from, in red are data from patients treated with breast cancer, and there is a strong correlation between the excess relative risk and the dose at the very high dose. But when we go at the very low dose, even if we can still see this correlation, we are not absolutely certain about if this correlation is really there. We have huge error bar. There is also this nice experiment that they've done with the twins, the Scott twins. So we have in space, in principle, just 559 humans, and the one that were in space for more than 300 days are just 8 astronauts. And you see that in principle here, in the end, the conclusion was about microgravity and ionizing radiation are the one that produce the most effect in the astronauts. And then when we have here predicted risk for 1 year Mars travel, then we see that the biggest problem, they become, you see here in green, we have irradiation, ionizing radiation in blue, microgravity, and then we have this mixed color. We see that the biggest problem are tumor development and cognitive decline. So possible shielding then. Galactic cosmic rays, in principle, they can go over 100 centimeters of in principle, any material. On Mars and Moon, the idea is to have passive shielding. For example, use material that, in principle, can be found on Mars or on the Moon. But in space, passive shielding, in principle, are too heavy. And heavy in space means money. Active shielding, the idea to use magnets, it's an idea, it's something that people are studying, but still we need more study about that. And then there are other alternative methods that we have seen before, but now we have probably even hibernation. So hibernation is not science fiction, it's something that in principle exists. Here there are represented different animals that can go in hibernation or something similar. So you have like torpor, that is a kind of daily hibernation. You have estivation, that is a kind of hibernation that happens during summer, for example, because of no water, and then the animal need to go in this kind of hibernation. Then we have hibernation, the proper hibernation, the one that it's a very long period of torpor. And then here we have brumation, that is something different, because in this case, this animal, they are not able to switch on and switch off their metabolism. So in this case, they just use the sun to increase their body temperature and to become active. So this one I would not consider in hibernation, but there are different mechanisms used, let's say, to protect themselves from stressor condition. Which kind of stressor condition? We have temperatures, we have food, we have predators. The physiological changes inside hibernators are different. I would be concentrated more on enhanced radioprotection, and we will see reduced metabolism, lymphocyte migration to the lymph nodes, preservation of muscle strength, preservation of bone mineralization. Hibernation is not let's say, quiescent state. During hibernation, here you see the temperature of the animal. Many times the animal have this arousal, so it kind of wake up many times. It's not really that he wake up and go for food or something like that, but it's the temperature increase again. The reason why this happen, it's not clear yet. Two explanations are: the first one, the animal need to sleep. Because during hibernation, in principle, the animal is not sleeping. And if you look at the electroencephalogram of the animal, in principle, it's like an active state, but very slow. So this is completely different from the REM, for example, or non-REM sleeping. Another explanation is, as I told you before, during hibernation, you have that the lymphocyte, they migrate to the lymph nodes. So there are no lymphocytes circulating. So it could be that during this time, the lymphocytes are going through the circulation, check for possible infection, resolve the problem, let's say, and then go back to the lymph node. Here we collect some data from animal hibernators, natural hibernators, and here we have rat. Rat usually don't go in hibernation. Rat are not able to go in hibernation. So here you see the same animal in the active state in red and in hibernation has an increase of radioresistance. They are more radioresistant. About the rat, even if you just decrease a little bit the temperature of rat, you have an increase of radioresistance. I try to summarize also the important information all this paper, and the first thing, temperature is an important parameter for increasing radioresistance. Summer animals compared to winter animals, both active and hibernating, were found to be less resistant. It was also a nice experiment where in principle they took cells from hibernators, they bring these cells at the very low temperature, then they take the medium of these cells and they move inside human fibroblasts, they irradiate the human fibroblasts, and they found an increase of radioresistance of the human fibroblasts. Like there is something in the medium that is able to protect those cells. There are broadly operative protective effects, no hematopoietic, gastrointestinal, and central nervous system syndromes, and an additional increase in survival occurs due to post-irradiation hibernation. As long as you keep the animal in hibernation after irradiation, more radioresistance you are able to see. Here there are also experiments with zebrafish, and here you can see those animals in a suspended state, suspended animation state. They did this, bringing the animal in an anoxia chamber before irradiation, and then they irradiate the animal in this suspended animated state. And you see here the control, suspended state, and then here no suspended state animal. And then you have a strong, in this case, increase of skin roughness in the not, let's say, hibernated animals. Also about the survival of these animals, in the suspended state, you have animals that still can survive, while in irradiated, without suspended state, the animals tend to die. With mice, they also did an experiment. Here, in principle, in the beginning, the idea was very nice. They use adenosine monophosphate. Adenosine monophosphate is, you know that ATP is the energetic molecule inside the body. So adenosine monophosphate is a molecule that in principle say to the body, look, you need energy. So you have no energy. In this case, the cells try to switch off their metabolism because they know that there will be some bad time about energy. So they try to use this molecule with mice, and they bring them in a hypometabolic state here. Also in this case, you can see that when they decrease the temperature of mice, and they decrease, and they use the adenosine monophosphate, they had an increase of survival of this animal. They had an increase of the white blood cells after irradiation. Here is the representative images of longitudinal section of femur harvested 30 days after irradiation. And then you see here the control. And then here again, you have a radioprotective effect when you use AMP. And this here is about the myeloid cells. Also in this case, you have a radioprotective effect. This, in principle, was a nice experiment, but at that time, people thought that mouse were not able to go in hibernation. Now we know that, in principle, mouse are able to go in daily hibernation or torpor. So when they use the same substances, for example, with rat, these substances didn't work anymore. Because then the rat had the feeling, let's say, that something was wrong, there was no energy, but there was no possibility for the cells in that case to switch off the metabolism in that case. So in that case, adenosine monophosphate did not work. As we said, during hibernation, we have an increase of muscle. I mean, we have no, let's say, weakness of muscle and bone demineralization. And there was this nice experiment where, in principle, they take winter bear serum and summer bear serum, and they put this serum inside human muscle cell, so human primary myotubes for 24 and 48 hours. What they found is when they used the FBS, so fetal bovine serum, the one that is usually used in cell culture, there was a difference when they used the winter bear serum because there was a strong increase of this myotube. So there was a really huge increase of the myotube, and also the degradation rate and lysosome and proteasome degradation decrease a lot when they use the winter bear serum in these cells. There was also a nice talk in Innsbruck. Sorry. Does torpor retard aging? And in principle, it seems that torpor, even at a high body temperature, it seems that stop the telomere shortening. That in principle is something that gives the aging. So in this case, Rob Henning in a TEDx in Groningen, using the mortality database from California and from Munich, he just said that in principle, if we have a woman born in the Netherlands let's say around the year 2000, if she would live, let's say, around 90 years in a normal situation, during doing, let's say, 6 months of hibernation per year, we could increase her life, let's say, almost double. So then hibernation can be interesting for space exploration. This is an artist's concept for Mars-ready habitat. And here you can see a very small space for 3 astronauts. Here you see the 3 astronauts hibernating. So then you have no cabin fever in this case, that it's due by claustrophobic reaction when a group of persons is isolated or in a solitary location. They will, let me say sleep, but not sleep because it's different, but they will sleep during the travel to Mars, let's say, or for deep space exploration to other planets and so on. So we can reduce the cabin fever. We can reduce food. Also in this case, food is weight. Weight is money. So if we can reduce the amount of food that we have to bring with us in the shuttle, of course we can save money. We can reduce the bone demineralization, the muscle strain. We can reduce the energy used, and it seems that we can reduce also the radiation effect. The question is human hibernation possible? Because the first experiment about hibernation, they started in the 60s when we had the first mission in space and the first mission to the moon. But then at some point they stop because they say, okay, nice. We know that hibernating animals are more radio-resistant, but we don't care. I mean, we are human. We are not able to go in hibernation. So the question is human hibernation possible? In principle, yes. And this is why in 2014, in the last 10 years, now also the Space Agency are again interested in the hibernation as possible solution. Here you see the different hibernation. We have hibernation, daily torpor, starvation, torpor, estivation in the order of mammals. You see, it's quite shared. So you have many animals in the different order that in principle they are able to do hibernation or something related to. If you go back to the common progenitor, you see that in principle during, let's say, the dinosaurs' time, there was one progenitor that was able to switch on and switch off his metabolism because he wanted to be, let's say, he wanted to be able to hunt and to be active when the dinosaurs were not active. When the dinosaurs disappeared because of this asteroid, in principle, those animals, they had all the time, let's say, to decide if they want to perfection this technique during doing, let's say, a very long hibernation like they do now, or just forget about that. But in principle, it could be that the mechanism is inside the cells, is still inside the cells. Still, in the ESA topical team, it was nice because they say during fetal life, birth and mammal are at the risk of hypoxia. And in adaptation of these, they are able to adopt some mechanisms that are similar to those of hibernating animals. And also during intrauterine life, the overall body size relationship of metabolic rate is switched off. And this is another thing that it's related with the hibernation. So yes, as I said, probably human hibernation, it could work. It was a few years ago that Matteo Cerri from the University of Bologna, that collaborated with us now in this experiment, developed what is called now synthetic torpor or synthetic hibernation. In this case, the synthetic torpor happened in rat. As I said before, rats are not able to go in hibernation. So the idea is to use GABA inhibitor, the mushimol, inside the raphe pallidus area. So at the moment, it's a quite invasive technique because you have to go through with the cannula inside the brain of the rat. But then doing this, in principle, you are able, here is the treatment plan, let's say 4 hours before irradiation, we start the inhibition with this mushimol, and then we had the temperature of the rat that decrease. Irradiation, total body irradiation, and then 4 hours after irradiation, we recover the animal, we sacrifice the animal, and then we did different tests. Here you can see also the brain temperature of the animal during the treatment. And here you can see infrared images of the rat inside the cage before treatment, when the treatment starts, and during treatment. So in this case, now you see that the temperature of the rats goes at the same temperature of the cage. There were also experiments in which, of course, the rats was recovered after irradiation. But for this test, because of ethical reason, we had to sacrifice the animal after irradiation. So in the next step, we hope to keep the animal for a very long time in hibernation, to irradiate the animal longer, and so on, to keep the animal longer after irradiation in hibernation. So the premises, of course, are to give the possibility to have, let's say, the space travel, starting, let's say, with hibernating animals to check for the metabolic pathway that are involved in that, and this to give the possibility to have space travel, and also, because, I mean, another thing why we can use hibernation is also in medicine. So here are some results that we had. So these are histological analysis of intestine and liver in normothermia, irradiated. Again, here we are irradiating full body irradiation. And then in synthetic torpor, you see a protective effect when we irradiate in synthetic torpor compared with the normothermia. Here you can see the vacuolization of cells that was detected in liver, but not in synthetic torpor. And more clear is in testis. Here is a representative images of the testis organization, and here is irradiation of in the normothermia, and here instead is irradiation in synthetic hibernation, where you see a quite protective effect. We did also some study. PCR-R8 gives you the possibility to study many genes together. So we studied the DNA damage signaling genes, and we find out that most of these genes are deactivated in the hibernators, like there is less damage. It seems like there is less damage. We check the hibernation genes, where in principle we have the same activation, deactivation of the genes that are also in the natural hibernators. And now we are working on the NGS. We have plenty of data of the NGS that we are analyzing, and soon we would like to publish also a work about all the data and the pathway that we find in the NGS experiment. Conclusion and outlook then, according to several studies from the 60s, we know that hibernation and hypothermia seems able to increase the radioresistance. It's not clear yet which is the reason why the animals become more radioresistant. One of the reasons could be that during hibernation, the animal breathes slowly, and then there is an increase of hypoxia inside all the tissue of the animals. This could be one of the reasons. Another reason, of course, could be some activation of particular pathway that we are going to investigate now, so hopefully we will find some answer about that. Human hibernation, in principle, could be possible. I mean, at least now we find out how to do synthetic hibernation in an animal that usually don't go in hibernation. Preliminary results confirm that also synthetic hibernation is radioprotective because, of course, I mean, we knew about hibernators, natural hibernators, but we know nothing about synthetic hibernation. So this was a preliminary study to confirm this. And more experiment, especially prolonging the synthetic hibernation, must be done. Of course, for this, we need to find good compromise for the ethical committee, and then this preliminary study, we hope, can give us the possibility to ask for a prolonged time of synthetic hibernation. We would like to do behavioral tests when the animal is recovered and so on. I would like to thank you, and I leave you with this picture from the Earth done by the Voyager 2 when was leaving, almost when was leaving the solar system. Thank you very much.
Thank you very much for this very interesting introduction about hibernation and opening of a new, totally new thematic of research to improve radiation resistance. So that closes these three presentations, close the keynote lectures. And we are very lucky to also have two young investigators, talented young investigators that now will have shorter presentation and will bring two different aspects that are also important for radiation protection. The first speaker is Dr. Bjorn Baslet from the Belgian Nuclear Research Center in Mol, Belgium, and he will speak about the Hindlimb unloading animal model in mice.
Okay, so hi everyone. As mentioned, my name is Bjorn Baslet, and I'm going to talk about the Hindlimb unloading model that we developed at the Belgian Nuclear Research Center in Mol in Belgium. Okay, thank you. So, as we venture into space, it's quite an extreme environment. We're exposed to a lot of different stress factors. As such, we can identify three prime stress factors. The first one being ionizing radiation, so we heard a lot about cosmic radiation we can find in space. But you also have the loss of gravitation. And the final factor is also psychological stress due to confinement and isolation, for example, on board the ISS. All these different space stress factors induce a lot of different human health effects. So we already observed some of them, like cardiovascular disease, but also fluid distribution changes and muscle atrophy. There are a lot of research questions still unanswered, and at the moment we're still looking into all of them. Some of them are, how do they affect our human health? And next, of course, them from occurring. Can we stop disease developing in space, and can we get our astronauts safe, for example, to the moon village or to Mars? As SEK, of course, we're also interested in helping answering these questions. And to do that, we have a lot of Earth-based analogs, where we can simulate the exposure to the space stressors. First of all, we have different modalities to simulate microgravity. As you can see to the right with the images, we have a rotating wall vessel as well as a lot of RPMs available at SEK, which simulate the continuous fall movement needed to develop microgravity. In addition, we also have irradiation facilities, either at SEK or in entire Europe or even there outside, for example, South Africa, where we can expose ourselves to different kinds of ionizing radiation. In addition, we can also simulate the third stress factor, which is psychological stress, by the addition of different stress hormones to our cultures. And we have done this already successful for a lot of different projects aiming at immunology, brain sensitivity, cardiology, and developmental biology. But the thing with this is that we can't really make a connection yet between our in vitro studies as well as our astronauts. So there should be some intermediate. This intermediate is the Hindlimb unloading model, in which we try to simulate a lot of these fluid distribution changes occurring in space due to a loss of gravity. So here, for example, you see an image in which a human ventures into space. When you go towards, for example, outer space, you will see that a lot of blood is collecting at the site of the brain and of the head, and not a lot anymore at the legs. And this is actually what, for example, simulated as well at the bed rest study, in which people has to stay in a bed for at least 60 days with the head down tilt, in which we also find these fluid distribution changes. This fluid distribution change also induces a lot of different effects in the human body. For example, a loss of muscle, a loss of bone, and even a disruption of the immune function. If we then look at the hind limb unloading model, it's a model that's already been going on or have been used since the 1960s, in which we suspend an animal. We can see here at the right. So an animal is suspended and is not unable to use its hind limbs to support its weight. This model, as mentioned, simulates as well the fluid changes we can observe in space. In addition, we can also observe other different facts like immune dysfunction, osteoporosis, even the breaking down of muscle tissues, and even nervous system problems. The model that we developed is non-invasive, meaning that we don't need any surgery to implement it in our animals, and we just use physiotherapy tape you can find in a normal pharmacy. If we take a closer look to our hind limb unloading model that we use at SEK, you can see, for example, the cage system we use. So we use a SPF, so specified pathogen-free condition, in which the cages are also individually ventilated. In addition, we have a low-friction sliding system in which we append our animal, so the animal can freely move throughout the cage and use the entire area. We tape the tail with this mesh friction tape or physiotherapy tape, and we also use a stretched and rolled folded metal at the cage bottom, so that the animals have grip to pull themselves with the cart throughout the entire cage. Of course, our animals need food and water, so it's not easy to use bottles to drink, but we use hydrogels, which is a gelatinous replacement of water. In addition, we also make use of their normal pellets for the animals. Finally, it also needs to be mentioned that this model is fully approved by the Ethical Commission, as well as our animal welfare body. In addition, we have a veterinary on site that takes control of the animals, and we also have caretakers that twice daily check these animals for health and survival. So if we conceive our space mice, we can also do a lot of different simulations. So we have ionized radiation, microgravity, and psychological stress in space. So we try to mimic this as well, these conditions in our animals, by irradiating them with different kinds of ionized radiation, putting them in the hind limb unloading position, as well as addition of stress hormones to the system. So in this respect, we have some preliminary data to show based on study performed in a normal adult C75 Black 6J mice. So here in this table, you can see our experimental setup. So the animals arrive at about an age of 10 weeks, in which we have first a quarantine week to see if they're that they're really specified pathogen-free. After quarantine of 2 weeks, we have an acclimatization period in which animals will be singly housed and kept at a higher temperature. After these 4 weeks, we have the start of the hind limb unloading condition, in which some cases we also added stress hormones to the hydrogel. Mid-term, so meaning after 7 days, our animals were irradiated 1 gray of ionized radiation, after which a second week followed and we sacrificed the animal. During the entire period, we collect a lot of different materials, and we have already set up a lot of network with other partners throughout Europe to collect different tissues of interest. Some of them are, for example, the brain, but also feces or bone and muscle tissue. Just to give an indication about the model itself, so here in the graph you can see the amount of food intake these animals do, and you can follow them throughout the entire hind limb unloading procedure. So you can see here that these animals, while they were standardized, they ate a little bit less, but when we go into the hind limb unloading, so you see a decline in the amount of food intake, that's day 1 of the hind limb unloading condition, it gives a certain amount of stress, but after a day this is compensated again. You can also see that the green, so meaning the control, and the red, meaning the HLU mice, ate the same diet, so they were diet paired. So all animals had the same amount of food intake at the moment of HLU start. In first instances, we wanted to know if the stress was induced by this hind limb unloading model. So what we did is we checked the fecal corticosterone levels, and you can see here on the graph that there was no difference in the amount of fecal corticosterone levels inside our hind limb unloading mice when comparing them to the control animals. Another indication of stress are also the masses of the adrenal glands. If you have a chronic stress state, the adrenal gland mass increases. Here again, you can see on the graph that there was no increase in the amount of adrenal gland weight, meaning that there was no chronic stress induced by our hind limb unloading system. Of course, we wanted to check as well if other factors were still affected like we expect them to be. One of the things we looked at are blood smears. So in blood smears, we can identify a lot of different immune system cells. So here we looked at neutrophils, lymphocytes, and monocytes, and we found that there were differences in the amount of these cells, meaning that they had an immune dysfunction when they were 2 weeks in this hind limb unloading condition, without the addition of corticosteroids, so stress hormones. Afterwards, when we found out that there was no stress induction, of course, we needed to induce stress in these animals because space is quite a stressful environment. So we added hydrogel and corticosteroid to the cages. In this graph, you can see, for example, the weights of two different muscles in the hind limbs of these animals, the gastrocnemius and the soleus. In this graph, you can see that the weights of both muscles decreased significantly, meaning 26% less and 47% less, respectively, for the gastrocnemius and the soleus muscle in these hind limb mice, which were irradiated and had stress hormones. In addition, we also observed a decrease in the amount of spleen tissue, or spleen weight, and thymus weight, indicating again that there was an immune dysfunction induced by the addition of the hind limb unloading process. Of course, this is not the only results we will collect from this network, so we are still interested in performing proteomics on the tissue samples we collected. We're also performing immunohistochemistry stainings to see the different effects on skin, for example, and the brain. We will also perform in the near future Western blots based on the metabolic exchanges we observed, and we also want to do some behavioral testing to see if the central nervous system function is also affected. So I would like to thank all of these people listed here for their support and for making it possible to perform this HLU study. Thank you very much.
Thank you. Thank you very much for this very interesting model of the hind limb. And we move now to the last presentation of today, given by Dr. Nissem Abdeljelil from the Faculty of Medicine in Sousse, Tunisia, and she will speak about bacteria. Thank you.
So this is the one to change slides? Okay.
Yes.
Where should I point?
In the middle, the white bar,
Okay.
and this is for the slides. If you want
It's okay.
to point.
Okay. Okay. Hi, everyone. I'm honored to be here today to represent my team and to present to you the results and our suggestions in front of such valuable scientists. It's okay? Okay. I'll be talking to you about not how to get protected from ionizing radiations, but how to use it in space to get protected from contaminations from bacteria and biofilms. So it's about a physical treatment of our strain of Salmonella and how it disrupted its key aggregation processes. We will start by some history. It's been about 3 billion years ago since the ancestors of bacteria have appeared on the planet Earth. And since then, actual bacteria is thriving everywhere. It's in your stomach, on the surface of your skin, but also in more extreme places like in the polar ice, the deep oceans, and in dry deserts, and even in dark caverns. So bacteria can be beneficial to humans. We use it in many industries, but it is also harmful and very often life-threatening, especially for people who are living and working in isolated places, like crews of submarines, manned space facilities, and teams that are in remote scientific or industrial stations. Especially because for these people, the health and the technical support is limited and is not always available. Okay. So, bacteria has tremendous skills in adapting to stress, and So it has tremendous skills to adapt to stress, and free bacterial cells, when facing harsh conditions, can choose to move from the free form or the planktonic form to a biofilm form. This biofilm form is about going into a multicellular community of bacteria and secreting a polymeric matrix, which they use to surround themselves and to protect themselves from the environment. This polymeric matrix is mainly composed of proteins and polysaccharides, and they hide inside it, and this way they become more resistant to many treatments with biocides or with antibiotics. So these biofilms can have can be certainly health hazards, but also they are a technical challenge, because when they form inside devices, they can clot the equipment and induce even the failures of the systems. And this can be very dangerous if you're alone in space surrounded by vacuum, or if you're in a submarine and you're immersed in deep waters. And it has already been observed. For example, here we can see the photos from NASA. We can see how biofilm formed inside the inlet channels of the water processor at the ISS. And at the right, we see how a biofilm clot is blocking the condensate plumbing always at the ISS. So our team was trying to find a solution for this general problem, because it's not only in space, by using an alternate method. We're not using, it's not based on a chemical process, it's based on a physical process. And now in industry, the chemical decontamination techniques are being anyway abandoned and replaced by techniques like ionizing radiations. So our strain, our bacterial model is a strain of Salmonella. We exposed it to 1 kilogray and 2 kilogray of gamma rays. And then we tested it for its biofilm capacity to produce a biofilm, and also did a proteomic screening in order to identify maybe what are the proteins or the molecular modifications that have been induced by the exposure to the ionizing stress. So our first result is that we noticed that the 2 kilogray ionizing radiation dose was more effective than 1 kilogray ionizing dose. So it inhibited the formation of the biofilm better than the 1 kilogray. And we noticed also that temperature has an effect, a big effect on the results, because here for the same material, for example, we used polystyrene to grow the biofilms. We have 100%, with the use of the 2 kilogray dose, we have a 100% of inhibition in 28 degrees Celsius, while it decreases to 93% of inhibition when we use 37 degrees Celsius. Despite this, we can say that the optimal conditions for this protocol were at 2 kilogray of ionizing radiation at the temperature of 28 degrees Celsius. So we did the proteomic analysis, and the proteomic analysis was in order to identify, as I said before, the genes or the proteins that were involved in the biofilm formation and has been affected by the ionizing stress. First of all, we can see that there is a protein who has been massively overexpressed, which is the protein that is expressed by the gene FLEC. It's a protein that is involved in the promotion of motility in bacterial cells. So maybe the interpretation, our interpretation here is that when exposed to ionizing radiation, the cells tries to move more than it tries to settle. So it promotes a pro-motility lifestyle. Then we have the gene FLGM, which was also overexpressed. The FLGM gene is a silencer of another gene, which is flea A. And flea A is the one directly involved in the biofilm growth. So when you inhibit flea A through the massive presence of FLGM, you would inhibit the biofilm formation. And this is in accordance with our results, where we find barely detectable biofilm formation in all samples. Next to this, there was another important protein who is involved in the biofilm formation, which is the PAPT. PAPT is responsible for the synthesis of spermidine, a protein which is involved, a central protein for bacteria that is involved in many functional phenomena or reactions in bacteria, and especially in the regulation of the biofilm formation. And this happens depending on the stress present in the environment. So here, as it was shut down, and we had no biofilm, no detectable biofilm formation, we speculate that the inhibition of the synthesis of spermidine is a way to promote motility rather than promote settlement. Then we go to this couple of genes, which is SPOT and REL-A. SPOT and REL-A are two proteins who governs the synthesis of a bacterial messenger called the guanosine pentaphosphate. The guanosine pentaphosphate presence in the intracellular medium is proportional to the biofilm capacity, the biofilm formation capacity of the bacteria. So when we inhibit these genes, it's like we're inhibiting the bacteria capacity to form biofilms, and this is what we found in our experimental results. Then we have also, we also noticed that also the lipopolysaccharides biosynthesis was inhibited. Lipopolysaccharides are important for the adhesion process of cells on a surface. They are involved in the surface colonization. So if we disrupt the biosynthesis of lipopolysaccharides, it will be difficult for the bacteria to be able to colonize the surface. So it's like we're inhibiting also these tools of aggregation and this tool of settlement into a biofilm for this bacteria. However, here we identified 8 genes that were pro-motility, lifestyle. 1 minute, okay, we end. Pro-motility, lifestyle. We, despite this, also found or identified 3 modifications in genes that were more considered for pro-settlement. These are the genes colored here. So the gene for the degradation of CDGMP, and the gene FLZ, and the gene for the chemotaxis protein. Conclusions. So, when this work, we identified 8 genes supporting the exposure to ionizing radiation repels surviving salmonella from settling on a surface. So if you have a critical components and you irradiate it to remove decontamination, maybe you have more chances that the bacteria won't settle in a biofilm structure again, because its settlement processes are being inhibited by the ionizing stress. Our suggestion here is that it could be possible to conceive or to design X-ray devices that could give X-ray devices to use on board the International Space Station, for example, because there are already commercial X-ray devices that we can have in a lab. So these X-ray devices may be used to decontaminate or to irradiate locally the components, filters, or some piping segments. And this way we will have a more efficient protocol than using chemicals This is what we are suggesting right now, and we are starting a collaboration with the Belgian Nuclear research center with Dr. Leis about this idea that we are trying to develop later. Thank you very much for your attention. Thank you.
Thank you very much. I would like to invite now all the speakers to join the round table, and we'll have certainly for a few minutes, let's say about 10 minutes of interaction between the audience and the speakers. So for the audience, please prepare your questions. So we'll start with your questions if you'd like. So is there any questions or comments? Yes, please. Is there a microphone available? There, please. There. Thank you.
Thank you very much. My name is Rudy Miner. I have a question to Christine especially, and maybe to some of the other speakers also. I haven't heard in all these lectures the word hormesis. Hormesis, the way I understand it, is that everything is useful at a certain measure. We need a little bit of water, not too much. We need a little bit of salt, not too much. We need a little bit of radiation, not too much. I know there are cities which have a natural, very high radiation level and where people get very old, maybe because of that. So I would like to know, is there a new level of hormesis or of radiation that is considered optimal, and maybe it's better to live in space than on Earth?
Oh yeah, here I can give a very long answer because it's such a complex question, and there are many experiments concerning the adaptive response that first irradiation with a low priming dose can protect from later high dose. But I would not rely on this for humans on a spacewalk exposed to a solar flare. So this is just not sure that it will help the human. So I would rely on proper warning and shielding of the effects. And concerning the stochastic effects, I really would say that there's no threshold. So the low dose exposures are very, very tricky to evaluate, but from the side of radiation protection, I would be very careful to say that we have positive effects. Even if we see an increase in growth of cells, it is something that is above the normal, and maybe it's not good. So it's how we judge these effects also. Even if we think it is positive, it might not be.
Okay. Well, okay. It's a nice question. There is also this population, for example, the one that they live in Ramsar in Iran, that they have a very high level of radiation because of radon. And for example, if you look inside that population, you find that there is a decrease, for example, of cancer. The point is really like radiation is healthy for them, or there is a kind of selection of this population inside that place. This, can be also another point of view, let's say.
Yes, a question in the back. Sorry, please.
Thank you. My question has to do with hibernation and also the ionizing radiation. It seems that if I'm understanding correctly, the reduction in sensitivity to radiation is not a physical manifestation of the cellular movements, intracellular movement of components within the cell structure, but you're looking for a biochemical pathway that actually you're looking for a series of chemical reactions that cause the desensitization and the through the mechanism of artificial hibernation?
Yeah. No, okay. In principle, first of all, here we did irradiation with photon irradiation. So we still don't know, for example, if we are able to protect the animals also with heavy ion radiation. About the mechanism, I mean, as I said in the last slide, in principle, it could be that there is, let's say, a physical, let's say, chemical process due to the absence of oxygen inside the cells. Mm-hmm. So we know very well that hypoxia increases the radioresistance. There is this oxygen enhancement ratio. So as much we go down with the oxygen, more radioresistance we have. So it could be that the animal breathing slowly increase the radioresistance inside the tissue. But I mean, since there are also experiments in which, for example, the one of the cold hibernator cells, the medium from those cells inside the human fibroblasts produce also an increase of radioresistance. Actually, in that case, for example, they check inside the medium to see which substances were present. And they found serotonin and dopamine that in principle should not be there because they are produced by the brain in principle. But they were there and they were somehow radioprotective. So the idea is there is probably some chemical explanation for this increased radioresistance, but probably if we look inside the molecular pathway, probably we can find something. So the idea of the NGS is a little bit like fishing now. So we want to see what is changing inside, and then if we find some specific pathway, then we look inside that, and then.
And this was a more esoteric question along that line. Has there been any investigation about reducing human physical, activity toward hibernation using, using meditation and techniques that bring on a less conscious, a less conscious level that's closer to hibernation. Okay. That might be bringing up the biochemical components that you're speaking of.
This, honestly, I don't know exactly how it can work. Another thing that, let's say, we know about this temperature-related and so on is, for example, that if you, after irradiation, you have, let's say, DNA damage and so on, and then even, let's say, if you have cold cells, in principle, you have more or less the same amount and so on. The difference is that it seems that when you are in this state of hibernation and so on, even the DNA repair mechanism, they work better. So it's everything slowly, but everything work better. I don't know exactly about this honestly I don't know so much. Yeah.
Thank you. Another question here, and then in the back. Yes.
This is a question to you again, Mr. Tinganelli from Kirill Pletner, the editor-in-chief of the Aerospace Journal. He's wondering if you've ever heard of a Buddhist monk who fell asleep while meditating. Basically, he's currently in Ulan-Ude. He has been asleep for 70 years under the ground, placed in a box, in a wooden box, and he seems to be alive. I mean, all of the bodily functions are working currently. So maybe it would make sense to study him to see how it works in terms of the hibernation mechanism. What do you think about it? Would it help to study his body to see if we could get to the right solution for traveling to the moon and to Mars, etc.? Thank you.
Yeah. Honestly, I didn't know about this story, honestly. And there are, let's say, other stories speaking about people, for example, a population of person in Russia that during the winter time they were able to somehow hibernating. But I think are more like metropolitan legend. I mean, I don't know about this person, and honestly, I don't know how to answer to this kind of question. Sorry.
Thank you. Yes, another question in the back.
Actually, mine is related in that there is scientific research that have shown that Zen meditation has affected the telomere length in terms of how it's affecting. And I was wondering specifically if anyone is doing research on the electromagnetic field, the actual fields that are shifting and generating by the organisms, whether they go into hibernation or whether as a mechanism to understand what might be actually happening. Because it seems that that is what these types of meditative practices are doing. They're affecting the way the nervous system is firing, and there could be something that's not happening necessarily chemically. And I just wonder if there's any research that's looking at how we're generating the field, and as that is a possible mechanism, and then obviously solutions as to ways to affect the radiation. I don't know if anyone had been exposed to any of that type of research or whether we could look into those pathways.
I don't know about this kind of study, honestly, so I don't know if some of you can add something.
I have access to some of the scientific papers, but
Yeah, so probably if you can share this one.
sure, because they showed that the telomere lengths are being affected, and it has been done with control studies and things like that. I just think that if we put more attention into that type of way, it might give us another mechanism by which we can affect these changes, especially in space.
Okay. I mean, it would be interesting to read more about that.
Absolutely.
What we know in hibernation, as I said, it's that you really can stop, let's say, the shortening of the telomeres,
Yeah.
the telomere. And actually, there is also the study now of the twins in space, the twins Scott, that actually what they found out that the brother in space, he had like, during the flight, he had an increase of his telomere, but immediately when he went back on the Earth, the telomere became immediately short, like the other brother, let's say. But I don't know any study about, the study you mentioned. So it would be nice to read something. Yeah. Thank you.
Yes, another question here.
Yes, I would like to ask everybody here more or less about the geometrical factor. When you talk about radiation, I think if you're free floating somewhere, you get it from all over, hemisphere, total global radiation. But when you land on the moon or on Mars or something, you immediately halve that radiation. I have never seen these factors that are shown that they say either you are on a surface with half or you are free floating, it comes from all directions. In addition, if you are on the Earth side of the moon, you get the shielding from the Earth. If you're on the other side, you have no shielding from the Earth. So, as you probably know, we all want to make a lunar village at the South Pole. Again, you have a different geometrical factor. That's my question. Geometrical factor, is it there or not? I haven't seen it.
Yeah, it's there. So I've shown the Mars data. And so this was comparable to ISS because we have the shielding by Mars itself, and it also has a thin atmosphere. So there we have this effect, and the moon is also traveling sometimes to the geomagnetic shielding of the Earth, so we have changes there. And so we hope to present these results soon because we together with the University of Kiel, we have a dosimeter on the Chinese LND Chang'e 4 mission. So it landed beginning of this year. And so we will have real measurements from the moon surface. This is very, very rare to have real-time measurements from the moon surface. And of course, we have the interaction with the surface and albedo neutrons, which are produced. So this also contributes to the dose on the surface. So it's a quite complicated calculation that has to be done to show all this. Yes.
Maybe a final question. Yes, in the back. Yes.
There the valence belt in Earth, and the ISS is under that, so that the radiation from the space is partially or rather blocked by this belt. But if you go to the moon, the voyage and moon base would have the without this valent band, so that they will have the strong radiational problems. Are there any protecting measures in the scientists to block this very strong space radiation. This is the first thing. On the on Moon, I think always this kind of radiation are falling out, so that on the Moon, do you have any measures to protect the human being from this radiation?
Or do you want to answer?
As you like.
Yeah. Well, you can
Please,
start,
please,
and
please, please.
but maybe to indeed the question about the moon and the irradiation on the moon is quite complex. So that there are different scenarios you can think about. Right now, it seems that most of the shielding would be using material and not so much the regolith. But we'll know more, I think, next week from the decisions that have been taken about the architecture of the moon village. Indeed, a certain layer of regolith would be certainly interesting. Maybe to dig and to have an underground facility would be also favorable. But then we hit other ideas and other issues, which are protection, planetary protection, and so that's an issue that we have to consider and we have to discuss with the protectionists for planetology. But right now we have quite a few materials that seem to be quite interesting for shielding, that are in the list that will be discussed this week about the architecture.
I see. So that the theme of this symposium is the fertility in the space, and as you know, this over or this during the development, they are very fragile to
Indeed.
the radiation. In that case, we should know the protecting measures, especially for this kind of the over or developing fetus from the radiation.
We've done some preliminary studies on the impact of radiation. We have a long history of studies on the impact of high doses of radiation on the embryo at all stages of development, during the embryonic development and then the fetal development. And what we see is that the highest risk at the early stages of development, just after fertilization, the highest risk is for cell death. It's for the death of the embryo. Whilst if you wait another week or two, you start to increase the risk of malformations, so abnormalities in certain organs, because the rate of division is extremely high. You have, as I mentioned, you have a rate of division of every 8 hours, and this has a kind of cost on the cell. The cost is that with this high speed cell division, you also decrease the high capacity of repair. So on one hand, you really have to shield or to protect better the embryo, and this is one of the reasons why they are more radiation sensitive. Then, because one cell can become a full organ, a full tissue, a full organ, so misrepair in in one embryonic cell can lead to an abnormalities. So this is very important to be careful to conduct this research. What was very striking in our preliminary research on the impact of weightlessness, simulated weightlessness, is that the embryo, as you know, just after fertilization, stays in this protective coat, which is the zona pellucida, for a certain number of days, and the zygote just after fertilization is one gigantic cell that will divide into smaller cells. So the cells will become smaller and smaller all through the migration of this embryo until the pre-implantation. So, and we see that in this, when you subject this embryo in microgravity simulated condition, you change the cell size and the cell morphology. So it's very important to carefully perform research using and combine stresses as presented. For example, radiation together with weightlessness and maybe stress. And I think the Hindlimb model that was presented could perform this kind of embryonic studies in pregnant mice and understand what is the impact all through the development. But I think it's careful studies that still need to be performed. But very interesting point.
Yes, I'm doing the artificial gravity, and we insist that the gravity is necessary in developing the fetuses. And this kind of the situation should also be applied for the radiation. So at the same time, in the small fetus, for the smaller fetus, radiation and microgravity should be bilaterally protected from these two kind of the stresses.
Yeah. Yes.
Thank you very much.
Thank you.
Thank you.
Thank you, all of you, and wishing you a good lunch. Maybe I ask Floris Wout to give the final word before we join the lunch.
Well, no, thank you. It was a marvelous discussion. We just overran 20 minutes, so I was proposed to start also 20 minutes after 2 instead of at 2 o'clock. But it was worthwhile because radiation is one of the key points of which we have to take care of when going to space, so it was very nice. Thank you so much for being here. Somebody, who else?
No, I don't know. So give to me, I will bring to them.
We have to remove
Oh, thank you.
Thanks.
Taking it so
Yes.